Today we'll explore how slow but relentless expansion has shaped not only the distribution of matter, but our very perception of the cosmos. Our journey begins with a simple observation. The horizon, whether seen from ashore or across the vastness of space, appears as a definitive boundary, a clean line that separates what is seen from what is not. This line, however, is not an end, but merely the limit of a perspective. Now, we will trace this concept outward, past the moon, past the planets, past the nearest stars, and even past the 2 trillion galaxies that are estimated to populate our cosmos. We scale this perspective across 13.8 billion years of space and time until we arrive at another horizon, a cosmic horizon. This one, however, is not a boundary that can be crossed. It is the absolute limit of what we can observe, a wall defined not by matter, but by light itself. While we have long wondered what else exists in the universe, a more profound question is where the universe itself ends. What lies beyond this ultimate edge? To understand this boundary, we must first establish our own position within the cosmic structure. We reside on a small, rocky planet orbiting an average star in a spiral arm of the Milky Way galaxy. For a long time, the galaxy's edge was thought to be a gradual dissipation into nothingness. Recent studies, however, have identified a more defined boundary to its star-forming disk, approximately 40,000 light-years from the galactic center, where the birth of new stars largely ceases. Our galaxy is one of the dominant members of the local group, a small cluster of around 80 galaxies. This group, in turn, is a minor component of the Laniakea Supercluster, a colossal structure of 100,000 galaxies interconnected by gravitational filaments. Our entire system is in motion, being pulled at over 600 kilometers per second toward a gravitational anomaly known as the Great Attractor, a dense region of mass obscured by the disk of our own galaxy. Even within our immediate cosmic vicinity, we find structures that defy simple explanation. A recently discovered cloud of molecular hydrogen, nicknamed Eos, exists just 300 light-years away. This transient structure is so immense that it would span the width of 40 full moons in our night sky, a cosmic ghost that will dissipate in a few million years. But all of this, every star and every galaxy we have ever recorded, sits firmly within our known world. To find the true edge, we must journey much farther, to the boundary of observation itself. Imagine an observer inside a space that has existed for a finite time. For light from a distant source to reach that observer, it must travel for a period no longer than the age of the space itself. Any light from a source more distant has simply not had enough time to arrive. This is precisely our situation. The universe began approximately 13.8 billion years ago. Therefore, the only light that has reached us is light that has been traveling for 13.8 billion years or less. This limitation creates a sphere of observation around us, with Earth at its center. This is the observable universe. This cosmic horizon is not a physical wall. It is a horizon of information. An observer in a distant galaxy has their own observable universe, with a unique perspective that includes regions we can see and others we cannot, and vice versa. When our most powerful instruments, like the James Webb Space Telescope, are directed toward this boundary, they do not see a cosmic wall, they see the past. As we look farther into space, we look further back in time. Observing an object a billion light-years away shows us its state as it was a billion years ago. When we extend our view to the absolute limit, we observe the oldest light in the universe, the cosmic microwave background, or CMB. This is the afterglow of the Big Bang, a faint radiation that permeates all of space. It originates from a period about 380,000 years after the Big Bang, when the universe was an opaque fog of hot, dense plasma. The CMB is the surface of that fog, the first light that was ever able to travel freely. In every direction, we see this ancient wall of light. It is the boundary of our vision. The central mystery, therefore, is what lies beyond it. The nature of this boundary is further complicated by a fundamental property of the cosmos, the expansion of space-time itself. This process is often illustrated by imagining dots on the surface of a balloon. As the balloon inflates, every dot moves away from every other dot. The dots are not moving across the surface itself is stretching. This is analogous to our universe. Space itself is expanding, carrying galaxies along with it. This has a peculiar consequence. An object whose light has traveled 13.8 billion years to reach us is now, due to this expansion, much farther away. Current measurements place the radius of the observable universe at approximately 46.5 billion light-years, making its total diameter a staggering 93 billion light-years. For much of cosmic history, this expansion was thought to be decelerating. However, in 1998, observations of distant supernovae revealed that the expansion is, in fact, accelerating. The cause is attributed to a mysterious component that constitutes roughly 70% of the universe: dark energy. Its nature is unknown, but it functions as a repulsive force, pushing space-time apart at an increasing rate. The European Space Agency's Euclid mission is currently mapping the cosmos in 3 dimensions to better understand how dark energy has shaped its structure. This acceleration creates an even more profound kind of horizon. There are galaxies so distant that the space between us and them is expanding faster than the speed of light. This does not violate relativity, as nothing is moving through space faster than light. Instead, space itself is stretching. The light from those galaxies is like a person attempting to run up an escalator that is moving downward faster than they can ascend. It will never reach us. These galaxies are beyond our cosmic horizon, their information irrevocably lost. The edge is not a destination, but a constantly receding, accelerating boundary from which no new information can ever arrive. This brings us to the theoretical realm, where direct observation gives way to inference based on the established laws of physics. On large scales, the universe appears to be homogeneous and isotropic, looking the same in all directions from all locations. Data also shows that the geometry of our universe is flat. In such a universe, parallel lines remain parallel indefinitely. The most straightforward conclusion from a flat geometry is that the universe is infinite. Beyond our observable horizon, there is simply more universe, an unending expanse of more space, more galaxies, and more dark energy. In this view, our 93 billion light-year observable bubble is an infinitesimally small patch of an infinite cosmos. What lies beyond the edge is more of the same forever. However, certain theoretical frameworks, such as cosmic inflation, the period of hyper-rapid expansion moments after the Big Bang, suggest a far more complex reality. Most inflationary models predict that the process is eternal. While inflation stopped in our region of space, allowing our universe to form, it likely continued in other regions far beyond our horizon. Imagine the greater cosmos as an ever-expanding block of Swiss cheese. The holes are bubble universes, like our own, where inflation has ceased. The cheese is the inflating space between them, constantly creating new bubbles. In this scenario, our universe is one of many, and in each, the fundamental laws of physics could be different. Other theories also point toward a multiverse. The many-worlds interpretation of quantum mechanics suggests the universe splits into parallel branches at every quantum event. String theory, with its vast landscape of possible physical laws, also implies a multiverse of universes with different properties. These concepts exist at the frontier of theoretical physics, compelling yet currently beyond empirical verification. They present a vision where the universe is merely one component of a much larger multiverse. Whether the universe is a lone, infinite expanse or one bubble in a cosmic foam, its long-term evolution appears to be dictated by the relentless push of dark energy. The accelerating expansion means that, over trillions of years, galaxies beyond our local supercluster will be pushed past our cosmic horizon. The night sky will grow darker as distant galaxies recede from view. The prevailing theory for the ultimate end is the Big Freeze, or heat death. In this scenario, Expansion continues until all matter is spread so thin that the universe becomes a cold, dark, and empty place. Stars will exhaust their fuel. Their remnants will become black holes, and even those black holes will eventually evaporate over incomprehensible timescales through Hawking radiation. All that will remain is a dilute void of stray particles. We began by considering a familiar horizon on a shore. We have journeyed across 93 billion light-years to a cosmic horizon we can never cross and explored theories that suggest an infinity of worlds beyond our own. We end in a cold, dark future where the universe itself fades into a state of maximum entropy. The question, what lies beyond the edge, does not yield a simple answer. It may be more of the same, stretching into infinity. It could be another universe with different physical laws. Or perhaps the question itself is flawed, as the universe, by definition, might be all that exists. What we do know is that this edge is not a destination, it is a mystery. And in looking towards it, we are not just measuring the scale of the cosmos, but the scale of our own curiosity.